Hi, so this will be the class on the consumer choice, and we will be continuing on the part that we have left on Monday. So what we have done is basically, so we have defined so far the preferences, and we have defined the utility function. Then we said that whenever we consider an indifference curve, okay, the slope at a fixed point, okay, slope at a point on indifference curve is represented by MRS, okay, and MRS is equal to the minus sign marginal utility. So let's say this is good X and this is good Y. Marginal utility of good X divided by marginal utility of good Y. Here the marginal utility of good X is d utility, okay, dx, and the utility dy. Okay, then we started with the budget constraint. Okay, and for the budget constraint, so you are given a fixed income, okay? And given this fixed income, so given this fixed income, we also have two goods. We have two goods here. So let's say good X and good Y. Then they have prices. Px is the price of good X, and Py is the price of good Y. Then we can write the budget constraint. It's basically is the bundles of goods that can be bought if the entire budget is spent on those goods at given price. Okay, so then we can represent the budget constraint with Px times X. Okay, so this is the price of X, this is the amount of X that you can buy, plus Py times Y is equal to Y. Okay. Okay, so in order to make things that we will not mix, okay, so let's say that so instead of Y we will denote income with I, and we will continue from there. Okay, so we can show this budget constraint on the graph again. Okay, so this is X, this is Y. So basically we will first want to find them the maximum amount of X you can consume, so which is attained when Y is equal to 0. So basically the maximum amount of X that you can consume is I over px. Okay, so this will be the maximum amount of x that you can consume. Similarly, the maximum amount of y that you can consume is I over py. Okay, then the budget line, budget constraint will be the line connecting those two extreme points. Okay, so this is the budget constraint, or which is also known as budget line. Okay, so in this chapter, okay, so our objective is which bundle, okay, maximizes consumers utility with given prices and income. Okay, so as you remember, okay, so let me draw it again. So if you remember the preferences, okay, so when we talk about the indifference curves, we told that so as the indifference curve goes up, okay, the farther the indifference curve from the origin, okay, the better it is. Okay, so for this question, so we would like to find the bundle on the most far away indifference curve, okay, that can be achieved with our budget constraint. Okay, so these orange ones are the indifference curves. Okay, so these are the indifference curves. So we would like to be far away from the origin. Okay, so this is origin, but we would like to have that bundle to be achieved under our budget constraint. Okay, so let's say that our budget constraint is this red one. Okay, this is budget constraint. Okay, so what we would like to do is we would like to find a point, okay, on this budget curve. Okay, okay, so let me continue with the second part of our reporting. So what we would like to do is we would like to find a point on this budget constraint, on this budget line, so which intersects with the uppermost indifference curve. Okay, so we would like to find a point on the budget line which intersects with the uppermost indifference curve. So why? So being on the budget line, okay, so let me write it here. Being on the budget line guarantees that point is that point can be afforded. That point is affordable. Okay, so uppermost indifference curve, on the other hand, uppermost indifference curve means that we achieve highest utility subject to our budget and prices of the goods. Okay, so let's take this point. Okay, so this point is on an indifference curve. Okay, but we can do better, okay, than this point A. Okay, we can do better than point A. The reason is we have more money. Okay, so it is not on the indifference curve. Let's consider this point B. Okay, so point B is giving us a higher utility. Point B gives us higher utility, but it is not affordable, okay, given our budget constraint. So what we would like to do is, in fact, okay, so remember there are many more indifference curves here, okay, so I haven't drawn all of them, okay. So there is an indifference curve, okay, so which intersects, okay, so there is an indifference curve which intersects with the budget line, okay, and any upper indifference curve cannot intersect with the budget line, okay. We need to find the indifference curve which intersects with budget line and any upper indifference curve cannot intersect with the budget line. Okay, so while we are looking for the upper indifference curve, so it will gives us higher utility. Okay, so this is some kind of a maximization problem here. Okay, so we would like to find this blue point C. Okay, so the good thing here is basically, so if our indifference curve are like this smooth, okay, at that intersection point, when the indifference curve is smooth at the intersection point, budget line and indifference curve are tangent to each other. Okay, so what does this tangency mean? That means that they have the same slope. Okay, so if you remember that the slope of the indifference curves can be represented by MRS, okay, which is the minus marginal utility of good x divided by marginal utility of good y. Okay, so if we write it better, it will be minus sign derivative of the utility function with respect to good x and the derivative of the utility function with respect to good y. So then what is the slope of budget line? So the slope of the budget line, okay, so let me show it on the graph. So when we consider this graph again, this is good x, this is good y. So let this be the budget line. So we know these two extreme points. The first extreme point is income divided by px. So this is the maximum amount of good x that we can consume. The second one is income divided by py. Okay, so here the slope of this line is basically this vertical part divided by the horizontal part. Okay, so the slope of budget line is with minus sign due to the shape. Okay, income divided by py. Okay, income divided by px, so which will be minus px over py. So this slope of the budget line is also called as marginal rate of transformation. Okay, and it's equal to the ratio of the prices with minus sign. Okay, then at this optimum point, okay, so if you think about this is the uppermost indifference curve that is intersecting with the budget line, okay, so which is tangent. Here MRS is equal to the ratio of the prices. So let's write it more clear. Okay, so it will be minus sign du over dx divided by du over dy. Okay, so this field gives us the optimum bundle. Okay, with in addition to that, we need to have this budget line. So let's do an example for that. Okay, so how do you find and how do you solve such a question here? Okay, so first of all, so let me remind you that so we have seen three different kind of the indifference curve. Okay, the first one is the straight line ones. So which has same slope on all points and which is straight line. Okay, like this. So this will be the straight line indifference curves. Okay, and the equation for that is basically the utility function for that is utility x and y is equal to some constant a times x plus b times y. Okay, the second one is the L shape indifference curves. And basically, so they don't have any slope. They don't have slope. So I will explain it in a second. And they are as from their name, so they will be like this L shape. Okay. So why don't they have slope here? So basically, they don't have slope at these corner points. It's not defined. Okay. At their corner points. And the last one is the smooth indifference curves. And it will be like this smooth. Okay. So this point, let's say that A and point B, they have different slopes. Okay. So let's consider an example. Okay, so we will consider an example with this smooth indifference curve. Okay, so the example for that is called Douglas utility function. And the equation for the Cobb-Douglas utility function is usually given as xy is equal to a some constant x to the alpha times y to the beta. So let's solve an example. So in this example, we have a Cobb-Douglas utility function. So our utility is given as, so we have two goods here is equal to 2 times q1 to the 0.6 times q2 to the 0.4. And the price of the goods are given as that the price of the first good is 4, the price of the second good is 3. And our income is given as 16. So our question is, find the optimal bundle. So this is a Cobb-Douglas utility function. And for this kind of the utility functions, okay, so our optimum can be found by, this is the indifference curve, let's say, and this is the budget constraint. So this is budget constraint, and this is the uppermost indifference curve intersecting with budget constraints. So for this kind of the indifference curve, for this kind of utility functions, so we can use the fact that, so at this intersection, okay, the slopes are the same. Slopes are the same. The slope of the indifference curve and the slope of the budget constraint, budget line, they are the same. So which means that margin rate of substitution is equal to MRT. Okay. So here MRT is the ratio, negative ratio of the prices, P1 over P2, and MRS is the negative sign, marginal utility of good 1 divided by marginal utility of good 2. So what is the marginal utility of good 1? Okay, so marginal utility of good 1 is the derivative of the utility function with respect to good 1. So which will be from this function 2 times 0.6 times Q1 minus 0.4 times Q2 0.4. So what is the marginal utility of Q2? Marginal utility of Q2, it is du over dQ2. It is 2 times 0.4 times Q1 to the 0.6 times Q2 to the 0.4. Sorry. Minus 0.6. So I will take the ratio of those two terms here. Okay, and I already know the ratio of the prices here. So the price 1 is 4, price 2 is 3, and the ratio will be minus 4 over 3. So what is left is, so I need to find this ratio. So if I look at the minus sign marginal utility of Q1, marginal utility of Q2, it is minus sign 2 times 0.6 times Q1 to the minus 0.4 times Q2 to the minus 0.4 divided by 2 times 0.6 Q1 to the 0.6, 2 times 0.4 Q1 to the 0.6, Q2 to the minus 0.6. If we do the math here, so 2 will cancel each other. We have 6 minus 6 over 4 times. I will take the Q1 terms to the denominator. Q1 0.6 times Q1 0.4. I will take the Q2 terms to the numerator. Q2 0.4 times Q2 minus 0.6. It will be minus 3 over 2 times Q2 over Q1. Okay. Then what I have so far, MRS is equal to minus 3 over 2 times Q2 over Q1, which is equal to the MRT, and I have already found MRT as minus 4 over 3. So if I do the math here, Q2 over Q1 is equal to minus 8 over 9. Minus Q2 over Q1 is equal to the minus 8 over 9. So if I leave Q2 alone, Q2 is equal to 8 over 9 Q1. So this is what I get from the slopes. Okay, but I haven't found the exact values of Q1 and Q2. So what I have found is just the relative values of Q2 in terms of Q1. How can I find the exact value of Q2 and Q1 here? Okay, do I have any other equation that I can use? The answer is yes. So we can use the budget constraint. Okay, so our budget constraint is the price of good 1 is 4 times Q1 plus price of good 2 is 3 times Q2 is equal to my income is 60. So I have two unknowns in the equation here, but I know the value of Q2 in terms of Q1. So what I will do is I will plug 8 over 9 Q1 instead of Q2 in this equation. Then I have 4 Q1 plus 3 times 8 over 9 Q1 is equal to 60. Then this will be 3. And let's multiply every part with 3. 12 Q1 plus 8 Q1 is equal to 180. So if we do the math here, so it will be Q1 is equal to 180 divided by 20, and it will be 9. Then what will be the value of Q2? So remember that so the Q2 is equal to 8 over 9 Q1. If I just plug in the value of Q1 here, this is 8 over 9 times Q1. I know the value of Q1 as 9, and it will be 8 over 9 times 9, so which will be just 8. Okay, so the optimum bundle will be Q1 is equal to 9 and Q2 is equal to 8. So my utility at the optimal bundle will be utility at 9 and 8 is equal to 2 times 9 to the 0.6 times 8 to the 0.4. Okay, so we don't care about the exact values of this optimum value. Okay, but you can check that so we are spending all our money at this optimum value. Okay, so basically, so if we just plug in here 9 and 8, so you will see that so if you plug in 9 and 8 here, okay, you will see that we are spending exactly $60 or 60 liras here. Okay. So that's all for today. Okay, so we will continue on Monday. So your TA will solve some extra questions in the recitation, okay, on Friday, this Friday.